So in this video, I will tell you about purlin design. In this video, we will take detail of purlin. Now, I have to decide we go through with SHS or Z section purlin design. Because this some people have confusion about this. Why we use Z purlin? Why we don't use SHS section, CHS section? Okay. So this Z section, C section basically have cold form members, and this SHS is hot form. Okay. This is basic difference between two sections. We use both of these for as a purlin. We have like as a purlin, but mostly we prefer this Z section. Why we use this Z section prefer for our PB? Then in this video we see in detail. We take some example. In that example, uh, at the end of this example, you can conclude that why we use Z section and why we not recommend SHS section for to our PV structures. So let's start. So first of all, this SHS or Z section we use for this uh, 7-meter base spacing. Okay, 7-meter base spacing we use. Okay, now let's start. Here some given data available for our analysis. Given data. First, Purlin spacing, Purlin span. Purlin span is equal to 7 meter, and spacing of rafter Purlin 7 meter. Spacing of Purlin. Spacing of Purlin is 1.5 meter. We have assumed. Roof slope. Here we consider roof slope 10 degree. Now sheeting. Sheeting we use galvanized steel sheeting. Provide lateral restraint to the top flange. This galvanized steel sheeting provide lateral restraint top of flange. Next point, location. Here we assume the location where the wind speed is moderate, okay, and very low load have considered. Now the design code we have used in this for this problem solve. For hot roll SHS section, we use IS 800 2007, okay, and for Cold-Formed Z Purlin, we use IS 801 1975. These both code we have prefer for different design. This IS-800 used for hot-roll member design or for IS-801 used for cold-form member design. Second point, in the second point, we will discuss about load calculation. Load calculation. We will conclude the load per meter length of purlin. For simplicity, we have concluded load per meter length. Whatever the load will come, we convert that load into meter per meter. So we will easily distribute that load onto the purlin. Dead load. Dead load. For dead load, the weight of sheeting and fixture. Weight of sheeting and fixture is equal to 0.15 kilonewton per meter square. Second point, self weight of purlin. Self weight of purlin. Self weight of purlin we assume 0.05 kilonewton per meter square. Total dead load will come, but if we add both of these, then we can get the value 0.2 kilonewton per meter square. Now kilonewton per meter square convert into the kilonewton per meter. So load on purlin will come, load on purlin is equal to 0.2 into 1.5. Here the 0.3 kilonewton per meter load will come on the structure on purlin. Second point, live load. For live load, we assume according to IS 875 part 2 of live load, the minimum roof live load are given 0.75 kilonewton per meter square. So we basically take this value for our purlin design. So load on purlin are 0.75 into 1.5. We get the value 1.125 kilonewton per meter. So this is load calculation. The dead load, live load, and third one is wind load. Wind load. For this, we have code IS 875 part 3 for simplify but representative calculation. Let's assume a moderate upward wind suction. Okay. We assume moderate upward wind suction. Volume will come minus 0.5 kilonewton per meter square. Now we convert this wind load, critical wind load to the kilonewton per meter. So load on purlin come minus 0.5 into 1.5 is equal to minus 0.75 kilonewton per meter. So this minus sign indicate this wind flow upward force. So these three main load we calculated: dead load, live load, and wind load. Here, the dead load, maximum dead load comes 0.3 kilonewton per meter, live load comes 1.125 kilonewton per meter, and wind load comes minus 0.75 kilonewton per meter. Okay, let's see IS 875 part 5 for load combination. The next point, our next point is load combination. For load combination, we see there are bending strength combination. Bending strength combination. Okay. For this bending strength calculation, we have two load, dead load plus live load, and second one is dead load plus wind load. So if this dead load, we see dead load plus live load. For bending strength combination, we generally use 1.5 dead load plus 1.5 live load. And here we actually use critical load combination, dead load plus wind load are 0.9 dead load plus 1.5 wind load. So 1.5 dead load plus live load, if we put both value in this, then we can get a kilonewton per meter value. Then 1.5 into 0, dead load is 0.3 or live load here come 1.125. If we add this and multiply with this, then we can get 2.14 kilonewton per meter. Kilonewton per meter value. This is downward. This force will act downward. And if we see 0.9 into dead load is 0.3 plus 1.5 and wind load will come minus 0.75. If we calculate both of these, then we can get the value minus 0.86 kilonewton per meter. So this is act negative sign. It means this force act upward. Okay, upward, or this is critical for uplift. Critical for uplift. Now we calculate both. We consider the general information, then we calculate the load combination, critical load combination for strength. And if you see the downward load combination govern for strength design. Okay, whatever the downward load coming or to the on the member, then it means the strength that member we have generally designed for strength. The upward load is critical for connection design. Okay, that means if suppose this member we have designed. Okay, suppose this member we have designed, and if basically the gravity load will come downward. Okay, so what we uh, means, if we want to stabilize this member, if this member have higher strength, then it can resist more load. Okay, so we don't want more connection, means more connection detail and uh, any other fabrication, but we want strength to this member for downward load act. But if we design the member against gravity, okay, this is member, but this on this member the load is coming upward. That means if this load is more act onto this member, then this member strength cannot much higher capacity to regain, means prevent this load. Okay, so that's why this member will easily fail or easily collapse. because of this uplift force. So for that, we design the connection more accurately to hold this member onto the position. So that therefore the connection detail is very important if we design uplift force. Or downward, in the downward is also connection design is proper, but we design member, if we increase the member capacity, then member can also withstand in the downward load also. So if we the upward load is critical for connection design, holding down the purlin. But for purlin member design, we will use the downward load. Okay. Basically, for purlin design, we use this downward load. We don't consider the upward load. So factor design load here will come 2.14 kilonewton per meter. Factor design load, because this downward force are more. Okay, this is 2.14. If you see, this is 2.14, and if you see, the upward force is critical, but this value is very less, minus 0.86 kilonewton per meter. So that's why we generally you focus on downward load. Okay, this 2.14 kilonewton per meter, this load. Now we start with first Purlin design, that is that is that is design of hot roll SHS Purlin. The code we use IS 800 2007. Okay, and SHS is efficient in biaxial bending. Okay, this SHS section have efficient in biaxial bending. And for a low slope roof, we can resolve the load into the component parallel to the principal axis of SHS. First one, bending moment. Bending moments. So for bending moment calculation, we have the formula for simply supported beam, WL square by 8. So W here will come 2.14 into 7 square divided by 8. The value will come 13.11 kilonewton per kilonewton meter. So this bending moment will come onto this hot roll section. The section we try the for this 13.11 kilonewton meter. Let's try SHS section selection. For section selection, let's try SHS 100 by 100 by 5. Okay, 100 deep, 100 wide, or 5 mm thickness. The section property of these are area is equal to 18.76 centimeter square. Moment of inertia Iz is equal to Iy is equal to 199 centimeter raised to 4. Section modulus Z is Zp Zpy. The volume comes 54.6 centimeter cube, or mass of this section is 14.7 kg per meter. Okay. Third point, check for bending strength. Check for bending strength. Check for bending strength. Here the design bending strength is MD is equal to beta B into ZP into Fy divided by gamma M0. If we see for plastic section, beta B is equal to 1 for plastic section, Zp is equal to the value is given, and Fy, if we use the hot roll section, that's why this Fy is equal to yield stress of steel Fe410 we use, Fe410, the Fy will come 250 MPa. Okay. Gamma M0 partial safety factor of material is equal to 1.1 for member design. Now MD is equal to 1 into 54.6 into 10 to the power 3 divided by into 250 in, Newton per mm square or divided by 1.1. If we calculate that this, we can get the value 12.41 kilonewton meter. So this value will more no, less than 13.11 kilonewton meter. Okay, so that's why this section is not acceptable. Which section? This SHS 100 by 100 by 5. Then we can increase this section size with for SHS 120 by 120 by 5. Okay, here the moment of inertia value 335 centimeter raised to 4. Section modulus is equal to 79.9 centimeter cube. Mass is equal to 17.7 kg per meter. Okay, here the value will come design moment MD is equal to 1 into 79.9 into 10 to the power 3 into 250 divided by 1.1. We get the value 18.16 kilonewton meter. So now we see this detail. Okay, MD is equal to 1 into 79.9 into 10 to the power 5 into 250 divided by 1.1. The 18.16 kilonewton meter, this value of moment will come. This value is greater than 12 point, okay, 12, whatever that value, 13.11 kilonewton per meter. So this section is suitable. Okay, this section is uh, feasible for our Purlin. Okay, now this section is okay. SHS 120 by 120 by 5. Now the second point is the second point is check for deflection. Check for deflection. If you want to check for deflection is nothing but check serviceability. Serviceability. Okay, serviceability. For this, for serviceability load, dead load plus live load. This combination we have 0.3 plus 1.125. Here the value come 1.425 kilonewton per meter. Okay, or the maximum deflection will come in Simply supported beam, the formula is 5 WL raised to 4 divided by 384 EI. Okay, here E is equal to 2 into 10 to the power 5 MPa. I is equal to 3.35 into 10 to the power 6 raised to 4. If we put this value into the given equation, then we can get maximum deflection phi. W value is 1.425 into L is 7 raised to 4 divided by 384 into E, 2 into 10 to the power 5 into I, 3.35 into 10 to the power 6. The deflection limit be this 3 into 7 into 10 to the power 3 raised to 4, because this all in mm. So the value will come 19.8 mm. This maximum deflection will occur in this purlin 19.8 mm. Or if we see this permissible deflection in purlin according to I100 is length divided by 180. Here the length will come L is equal to L value 7000 divided by 180. The permissible deflection will come 38.9 mm. Okay, this is it's okay. This is 38.9 permissible, but deflection come 19.8. So it's permissible. Now, this is final SHS section, or the weight of this SHS section 120 by 120 by 5 mm. This section have weight 17.7 kg per meter. Now let's see Z Purlin. Okay, Z Purlin. If you see this Z Purlin, for this Z Purlin, this is cold-formed section are thin wall and subjected to local buckling. Just like SHS section have higher capacity of biaxial bending, in this cold-formed section have thin wall and they can have local buckling. Their design is more complex. If you see, the Z Purlin design is more complex and involve calculating the effective section modulus. But in some manufacturer table, this effective section modulus is also given, which is less than the gross section modulus. Whatever the gross section modulus will come, this effective section modulus is less because this section have local buckling. So first point, bending moment. For bending moment, the formula will same, m is equal to WL square by 8. W value is 2.14 into 7 square divided by 8. The value come 13.11 kilonewton meter. Okay. Second point, we use section selection. For section selection, we have Z section of 200 by 19 by 2 mm section. Okay, here the nominal depth is equal to 200 mm. Flange width is equal to 75 mm. Or lip, here lip is equal to 19 mm, or thickness is equal to 2 mm. The material grade here Fe450. That means grade E450. Here the E450, it means Fy is equal to 450 MPa. Let's start the section modulus. Here Ixx value came 580 centimeter raised to 4. Z gross is equal to 58 centimeter cube. Area is equal to 8.95 centimeter square. Now the third point is check for bending strength. Check for bending strength. This is check for bending strength means considering lateral torsional buckling. We have considered lateral torsional buckling. Lateral torsional buckling. That's why we check for bending strength. Since the sheeting is attached to the top flange, it provides lateral restraint, preventing it because of we provide this purlin above the rafter. So this top flange have laterally restraint, provide lateral restraint. So that's why they're preventing LTB. They prevent LTB, lateral torsional buckling. We only need to check the section capacity based on effective width. Now the formula for bending strength is equal to effective section modulus into Fy divided by gamma m0. So here gamma m0 1.1, Fy value 450, and effective section, the value of effective section, the effective section we want, if we want to effective section calculation, then we can use as 801. In that, this involves checking for buckling of the compression flange and web. For this example, let's assume from detailed calculation. Okay, let's see. We use 0.Z effective is equal to 0.85 into Z gross. So 0.85 into Z gross, the value will come 49.3 centimeter cube. This value is Z effective. 49.3 into 10 to the power 3 into 450 divided by 1.1. The value is come 20.17 kilonewton meter. The section bending moment capacity is 20, but in our structure the bending moment come 13.11. So this section have more bending moment capacity. That is okay. This Z Purlin is okay for this. Now let's see check for deflection. Okay, this check for deflection. Let's see serviceability. Okay, for serviceability load, Ixx is equal to 5.8 into 10 to the power 6 mm raised to 4. Delta max is equal to 5 into 1.425 into 7,000 raised to 4, 5 WL raised to 4 divided by 384 EI, 2 into 10 to the power 5 into 5.8 into 10 to the power 6. The deflection value will come 11.4 mm. Okay, and permissible deflection is permissible L divided by 180, 7,000 divided by 180. the value come 38.9 mm. So this 39.9 mm, this is greater than 11.4. That is okay. Okay for deflection also. So this Z Purlin, okay, if you see this Z Purlin, we use Z 200 by 19 by 2. This have weight will come of this 7.02 kg per meter. Okay, so almost double load will come in SHS section. That's why this Z section is more economical and strengthen or serviceability also very good is compared to SHS section. So that's why we generally focus on Z cold form member for our purlin or girt design. Okay, because this uh, Z cold form member have higher capacity as compared to hot form members. Stiffness also very high as compared to hot form members. Now, every perspective we have conclude both this value and we have get this result. Now you can understand this uh, and clear about section selection in purlin or girt. Why we use Z purlin or cold form member for our structure. Hope you enjoy this lecture. We will meet in next lecture.